All right, let's jump right in. Today, we are cracking open a cosmic detective story, a mystery that we humans have been wrestling with for centuries. We're going to follow the clues that led us to understand one of the most basic, yet most powerful forces in the entire universe, gravity. And our investigation? Well, it kicks off with a really strange clue that had skywatchers scratching their heads for ages. So here's the first big puzzle. Early astronomers are tracking the planets, right? And most of the time, they drift steadily in one direction against the backdrop of stars. But then, things get weird. A planet will seem to slow down, stop, and then actually move backwards for a bit before carrying on. This bizarre celestial dance was the mystery. They called it retrograde motion, or in the old texts, moto retrogrado. So what in the world was going on? The very first big attempt to solve this puzzle was, well, it was based on what felt like pure common sense at the time. This led them to the geocentric model, the modello geocentrico, which put Earth right at the center of everything. I mean, it feels that way, doesn't it? But to explain that weird backward motion, astronomers had to add these extra layers of complexity. They dreamed up this idea of a small circle, the epiciclo, that a planet would trace, while that little circle itself rolled along a much bigger circle, the differente. It kind of worked, but man, was it complicated. And in science, when things get that clunky, it's usually a huge red flag that you're probably on the wrong path. Then came Nicolaus Copernicus, who dropped a bombshell of an idea, the modello heliocentrico, the sun-centered model. And this was a total game changer. Suddenly, everything clicked into place. By putting the sun in the middle, that strange backward motion wasn't strange at all. It was just Earth on its faster inner orbit overtaking another planet. Think of it like you're in a car on the inside lane of a racetrack, lapping a car on an outer lane. It was simpler, it was more elegant, it was a huge leap forward. But hold on, our detective story isn't over yet. Not by a long shot, because even with the sun at the center, a new problem popped up. The math. It still didn't quite line up with what astronomers were actually seeing. See, everyone was still clinging to this ancient Greek idea that the heavens had to be perfect, which meant orbits must be perfect circles. But the data just kept saying nope. The model was way better, for sure, but it still wasn't quite right. Solving this final piece of the puzzle needed a new kind of detective. A brilliant, incredibly stubborn mathematician named Johannes Kepler. After years of just grinding away at the data, Kepler finally cracked the code. He came up with 3 incredibly elegant laws. First, and this was the big one, he figured out planets don't move in circles at all. They move in ovals, or ellipses. That's his law of elliptical orbits, the leggi delle orbiti ellittiche. Second, he realized planets actually change their speed. His law of equal areas, the leggi delle aree, showed that a planet moves fastest when it's closest to the sun and slowest when it's farthest away. And finally, his law of periods, the leggi dei periodi, was the beautiful mathematical formula that perfectly connected a planet's year to how far it is from the sun. Case closed. Right? Well, not quite. And this is where the mystery gets even deeper. Kepler gave us the how. He laid out the rules of the road for the solar system with perfect, flawless accuracy. But he couldn't tell us the why. What was this invisible force pulling on everything, shaping those orbits, and making the planet speed up and slow down? What was the engine driving this whole cosmic machine? And for that answer, we need to turn to the absolute titan of our story, Isaac Newton, who was about to reveal a secret that applied to the entire universe. Newton came up with his law of universal gravitation, the leggi di gravitazione universale. And the idea at its heart was just breathtaking. He realized that the force pulling an apple from a tree to the ground was the exact same force holding the moon in orbit around the Earth, and the Earth in orbit around the sun. It wasn't just for planets, it was for everything. It was universal. This one single law explained it all. Now, Newton's brilliant equation had this one crucial piece, a number he called G, the universal gravitational constant. Think of it like the master volume knob for gravity across the entire cosmos. He knew this number had to exist, but the force of gravity is so unbelievably weak on a small scale, he had no way to actually measure it himself. So the case had a crucial piece of evidence missing.
It would take more than a century before anyone could find it. Then, in 1798, a guy named Henry Cavendish, using this incredibly sensitive and clever device called a torsion balance, a bilancia a torsione, finally did it. He managed to measure the tiny, tiny gravitational pull between two lead balls right there in his lab. His experiment was so precise that it essentially weighed the Earth for the first time and finally gave us the value for g. Newton's law was complete.
Okay, so this isn't just some dusty old detective story from history books. These laws, these discoveries are the absolute foundation of our modern technological world. In fact, you rely on them every single day. You ever use GPS? Check the weather? Watch satellite TV? Every single one of those satellites, including the satellite geostationary that beamed down our communications, was put in its exact spot using Newton's laws. His math tells us everything, from their basic motion, the moto dei satelliti, all the way to the precise escape velocity, the velocità di fuga, that a rocket needs to hit to break free from Earth's gravity and explore the cosmos. And we've gotten really, really clever at using gravity. Take the slingshot effect, or effetto fionda. This is pure genius. We send a probe, like the Voyager spacecraft, flying past a huge planet like Jupiter. It uses the planet's gravity to get a massive speed boost and get flung out toward the far reaches of the solar system. It's like playing cosmic billiards, and Newton's laws tell us exactly how to aim our shot. So what's the most extreme example of gravity you can find? That would be a black hole, or buco nero. This is what happens when you crush an unbelievable amount of mass into a tiny, tiny space. Gravity becomes so powerful that the escape velocity we talked about, that velocità di fuga, becomes faster than the speed of light itself, which means nothing, not even light, can get out. It's the ultimate cosmic prison. And yet, even Newton's perfect universe-spanning theory left us with one last, profound, mind-bending question. His law implies something called action at a distance, azione a distanza, meaning if the sun were to just vanish, his math says the Earth would instantly know and fly off into space. But how? How can a force act instantly across millions of miles of empty space? How does the sun talk to the Earth? Solving that puzzle would take another detective, Albert Einstein, and his radical new idea of a campo gravitazionale, or gravitational field. But that's a story for another explainer.